I'm Christina Corbane. I work at the Joint Research Center of the European Commission. Please let me first introduce a few words about the Joint Research Center, or the JRC, which actually sits at the crossroad or at the intersection between science and policy. It has a great mission that is driving the organization, which is the knowledge provider at the core of the European Commission. It's actually partnering with different policy departments of the European Commission to operate knowledge centers, which bring together different scientific expertise in different domains. And the aim of these knowledge centers is to help decision makers to better understand the latest scientific evidence in a concise but also transparent way. I work within the Knowledge Center for Disaster Risk Management, which is actually dealing with big Earth data, in particular Earth observation data, to feed into public policies for sustainable Earth. Speaking about Earth observation data, currently there's a big challenge to turn Earth observation data systematically and consistently into global information layers and into evidence on which to base key policy decisions. And this challenge is facing the Earth observation community in general, but at the JRC in particular. I will try in this talk to show examples of challenges and opportunities in developing an inclusive approach for using artificial intelligence to create new pathways for Earth observation data analytics and to respond to high-level political priorities, in particular the Sustainable Development Goals and the new urban agenda. So the world of Earth observation is currently witnessing dramatic changes that are essentially driven by recent advances in sensors, but also in digital technologies. There's an increasing need to mine the large amount of Earth observation data that's currently delivered by satellite sensors, new generation of sensors, and in particular by the Copernicus Earth Observation Program, which is delivering free and open Earth observation data to monitor the status of the Earth and its changes. Artificial intelligence is definitely one part of the solution by enabling scalable exploration of big Earth data. So by processing Earth observation data faster and on larger scales, artificial intelligence is actually pushing the boundaries of Earth observation data analytics. So in the light of the growing importance of artificial intelligence, our new president-elect has put forward political guidelines to prioritize investments in artificial intelligence. Most of all, the new agenda for Europe is actually putting or placing people at the center of the artificial intelligence development by piloting a process on the ethics guidelines for trustworthy and human-centric artificial intelligence. So with these political guidelines as a backdrop, we are trying to develop at the JRC a prototype for human-centric artificial intelligence in the framework of the global human settlement layer to support the reporting framework of the Sustainable Development Goals and other also important reporting frameworks of the post-2015 international agendas. The aim of this prototype is to answer to questions that still pertain to our fundamental knowledge about the spatial process of urbanization, and to answer questions such as what is a city, very fundamental, simple questions, or an urban area, what is the size threshold of an area to qualify as a city, and how do we distinguish urban areas from villages and towns and suburbs. At the Global Human Settlement Layer, the GHSL project, where I work in, we're trying to help to answer these questions by providing big data for policies. So briefly speaking, the Global Human Settlement Layer provides global spatial information and knowledge describing the status and dynamics of human settlements, both in terms of built-up areas and populations. It's also a platform integrating different information sources and different data sources, including population census data, socio-economic data, but also environmental data sets, and providing new evidence for decision-making to support the post-2015 international agendas, in particular the SDGs, but also the Sendai Framework for Disaster Risk Reduction and the New Urban Agenda. It also operates in an open and free data access policy, using open inputs and open methods and producing open outputs. And one of the key characteristics of this project is that it ensures, we are sharing the in-house developed tools for machine learning and big data analytics in a way to ensure reproducibility of the results and to facilitate information sharing and the collective knowledge building. So although the World Urbanization Prospects of the United Nations provide country-level information on the share of urban population, they don't provide information on the distribution of this urban population or on its changes or changes in the land cover, urban land cover. Our work that builds on Earth observation data complements the reporting of member states by providing spatially explicit information on human settlements and their dynamics. The arrows here are pointing to the cities that are reported in the World Urbanization Prospect in the universe of cities that are identified using Earth observation data. So the global human settlement layer, with its open data, open methods and tools, is engaged in an international commitment involving different stakeholders, in particular UN Habitat, to develop a harmonized people-based definition of cities and rural areas, and to support the reporting of several SDG indicators related essentially to SDG 11 on sustainable cities and communities. This definition will be discussed at the next plenary of the UN Statistical Commission, and if adopted, it will be crucial for guiding development aids for rural and urban areas, and also for targeting and guiding future census surveys. It's important also to mention that several of the indicators of the SDG 11 are highly sensitive to where the boundaries around the cities are drawn, and there are around 80 indicators in general that have an urban component. This is only an example of a couple of indicators that are sensitive to the definition or to the spatial delineation of the cities, such as the average share of built-up area of cities that is open space for public use for all. So to support the decision-making framework, the Global Human Settlement Layer has adopted a 4-level task, including the collection of structured and unstructured data that I call here level 0 data, which can be remote sensing data, but also population census data, crowdsourced data, and then producing standardized baseline data sets out of this unstructured data, such as built-up areas and population grids, using in-house machine learning, but also statistical induction, and then generating insights by analyzing this level 1 information and assimilating them into models such as the settlement model, and then disseminating the generated insights to different stakeholders, in this way closing the gap between data and action on the word using this hierarchical data processing paradigm. The components of machine learning and spatial modeling represent here the prototype of the human-centric artificial intelligence. I will now provide some insights into the value chain process with presenting a bit the GHSL basic concept, the Global Human Settlement Layer basic concept, starting from the Earth's surface to pixels to built-up areas. So the pixel here represents the fundamental unit for data collection from the Earth's surface. Using our in-house developed methods for automatic information extraction, we are able to map built-up areas. And built-up areas represent here all man-made constructed objects which can correspond also to permanent but also temporary shelters. So they represent not only buildings but also other infrastructure that are used for production of goods by people. So in 2015, or 2016 actually, the first public release of the Global Human Settlement Layer included multi-temporal built-up grids organized in 4 epochs, 1975, 1990, 2000, and 2014. These maps were produced from Landsat data archives. The Landsat is a satellite mission that's operated by the American Space Agency, and thanks to a consistent assessment of built-up areas over time, we were able to analyze the dynamics and evolution of human settlements over the entirety of the landmass. More recently, we have trained around 1,500 convolutional neural network models and applied them to a global data set of Sentinel-2 sensor. The Sentinel-2 is provided by the Copernicus Earth Observation Program. It's operated by the European Space Agency. And the results here show how, thanks to greater spatial detail of the Sentinel-2 compared to the Landsat and to advanced machine learning methods, we are able to shed lights on sparse and scattered built-up areas in rural Africa. In this case here, it's Nigeria. So you can see the output here from the Landsat, the first release of the GHSL, and this is what we can now observe thanks to the Sentinel-2 that is analyzed using CNN models. So the production of built-up grids at global scale is not only enabled by artificial intelligence tools, but most of all by large computing capabilities. So in terms of artificial intelligence tools, we are using our in-house machine learning classifier, the symbolic machine learning, which is a supervised classification framework which provides a scalable solution for large and complex multiple satellite scene data processing tasks. We are also using more well-known approaches such as the convolutional neural networks, but that we have trained in-house, and we adapted also to the processing of very high-resolution satellite data. But the execution of these data-intensive processing chains is enabled essentially by a large-scale computing infrastructure, the JRC Big Data Platform, and Pierre Swal is present here. He's leading the development of this infrastructure. It's a high-throughput computing infrastructure that, with the capacity to support scientific investigation on big Earth data scenarios. I will show here an example of a transition from the input satellite imagery to human settlement classification. And this is a case of a Landsat imagery acquired in Bangkok in Thailand. And thanks to machine learning, the symbolic machine learning in particular in this case, we are able to map built-up areas. And here this is the case of the density of built-up areas at 1 kilometer square. Using the built-up area grids, we are able then to derive population grids by disaggregating census population data according to the presence or absence of built-up areas in 1 kilometer grid cells. Then, using both the built-up grids and the population grids, we apply a harmonized definition of cities, the degree of urbanization, which is actually based on a set of criteria combining both population densities but also the built-up contiguity, to define three main spatial entities: cities, towns and suburbs, and rural areas. So the output of this process is a globally consistent settlement model that identifies more than 10,000 cities around the globe, and this map here shows the distribution of those 10,000 cities. And this is an example of a thematic policy-relevant application to measure the land use efficiency indicator 11.3.1, which is actually measured at the ratio between land consumption rate to population growth rate. And when compared here globally, it seems that the cities of the world seem to follow different sustainability trajectories depending on their income group, with low-income cities having more vertical trajectory compared to high-income cities which have a horizontal trajectory when analyzing the evolution of the population with respect to the changes in the built-up areas. So for the deployment of a successful artificial intelligence or human-centric artificial intelligence, it's important to take into account a process which is here represented as a co-design in which the technical development goes in parallel with the decision-making process and important landmarks in the political landscape. And this is the schema that we have adopted at the Joint Research Center and the GHSL project for the development and evolution of our methods, of the tools and all the data sets that we are producing that are all actually rely on a participatory approach involving different stakeholders, including international organizations, national authorities, but most importantly, national statistical offices that were engaged in this process through regional workshops we have organized in 83 countries of the world. I would like to share with you here a set of recommendations which were already seen previously in diverse reports, but this is in particular, these recommendations were put forward by a community of experts at the JRC, and they are summarized in a flagship report on the artificial intelligence, a European perspective. Most importantly, one of the key recommendations is that artificial intelligence for Earth observation in support to policies holds a promise actually for a revolution. But this revolution is more likely to occur rapidly if we are able to develop human interpretable solutions and artificial intelligence applications that are transparent, comprehensible, monitorable, and accountable. And I think this kind of work is a good direction towards the development of such artificial intelligence, human-centric artificial intelligence. It was recently published in Nature Communications a few weeks ago, and where the role of artificial intelligence in achieving the SDGs has been analyzed across the 169 indicators and the 17 goals, and where artificial intelligence was actually assessed as not only an enabler of the indicators, but also can be inhibitor. And I would invite you to have a look at this paper, quite interesting paper. And I would like to thank you for your attention and invite you to visit our website to know more about the data sets, about the methods and the tools, and about the global definition of urban areas and cities. And draw your attention to a special call on big Earth data intelligence, the convergence between big Earth data and artificial intelligence that we want to publish in Big Earth Data Journal. Thank you.